Hi, so I'm Amy. Today we're going to prove that there are infinitely many primes. I started writing some stuff up there just so that I can spend more time talking to you and not as much time looking back there. So the thing we want to prove, the claim, is that there are infinitely many primes. And we're going to do this by contradiction, which means we start by assuming the opposite of what's true, and we show that that causes a problem. And when it causes a problem, it means the original statement was true. So we start by assuming the opposite, which is that there are finitely many primes. So for some integer n, there are n primes, and we can list them out in a finite set. So this is our finite set P, which contains P1 through Pn, which will be our list of all of the primes, assuming it's finite. This is a capital P, those are lowercase p's. Oftentimes we use P to represent a prime in number theory. When we have already used P, we'll use Q instead. So we might run into that as well. So if we assume we have these primes, let's take these numbers and we're going to make a new number from them. So our new number, we'll call it M. And M, we're just going to create by making it be the product of P1 times P2 all the way through Pn. And then we're going to add 1 to that. So M is this product plus 1. Or if you're familiar with this notation, you can also write it as, this means the exact same thing, the product from I equals 1 to n of Pn plus 1, and the plus 1 gets added after. It's not within that product. So M is clearly not one of these primes in this set. It's bigger than that set. So M is not a prime because it's not here. So since M is not in the set P, M is not a prime. Because we're assuming we listed out all the primes previously. So since M is not a prime, it has prime factors. Every number is either a prime or has a prime factorization. Even a prime has a prime factorization, it's just itself. So since M is not in P, it's not a prime, so M has some factorization, Q1, Q2, times QK. So that's for some, integer K. And where all of the Q's are primes. And to be thorough, I'm just going to put that there. So these don't have to all be unique primes. It could be 2 times 2 times 3 times, like the primes could be repeated, but M will break down to a bunch of primes. So none of these primes are in this set, because if one of these primes were in this set, then when we divided M by that prime, we would get a remainder of 1, just because of the way that M is constructed. So none of the primes from P, capital P, this set here, divide M, because they all give a remainder of 1. When we divide M by them. So then what this means is that if none of the primes from P divide M, it means that all of our primes in our factorization here are not in this set. There are other primes. So thus, Q1, Q2 all the way through QK are not in our set P. So what this means then is there are primes that are not in the set, but we had assumed that this set contained all of the primes. So in particular, i.e., P does not contain all primes as originally assumed. I'll get shorter. And because of that, we've reached a contradiction. We've contradicted our initial assumption, which means our initial assumption can't be true. So what this means is the opposite has to be true, that there are not finitely many primes. In particular, there are infinitely many primes. Thus, there are infinitely many primes. And I know it might seem a little tedious when I say something and then I like write it and slowly say it again. When you write a proof, you have to write out all the words, all the sentences. There's a little bit of glare going on, but it just says, thus, there are infinitely many primes. So hopefully this helps. And thank you for watching.